When we are training a model for neural machine translation, sometimes one or both of the source and target languages we want to train do not have a lot of available training data. This is a low resource problem. So if you look at the steps for training a model, you need input, and that input is usually in the form of a parallel corpus of text in the source and the target languages. And if you do not have that text, that parallel text, where you have text in the source language that aligns with text in the target language, then it is going to be harder to train your models. So what do we do to train in these low resource environments? This is an ongoing research question. How do we perform quality translation when one or both of the source and target languages do not have a large corpora of parallel training texts available for us to train our models? Solving this low resource problem requires some creative approaches. And here, I'm going to go through some common techniques that you'll find. In data augmentation for natural language processing, we find techniques for data augmentation for translation data. In data augmentation, the goal is to generate new synthetic data that is based on the available natural data. So we want the synthetic data to closely resemble the natural data and able to have the synthetic data be added to that data corpus of the natural data to augment the data available to us for training. And so in the following techniques, you have to consider the language pair in question and be careful not to over-augment. So that's something to be aware of as we're going through the techniques. Or choose the wrong technique, which may lead to nonsensical training data. So the goal is not only to augment the training data so that we have a larger data set, but while we're doing so, ensure that the new data that we're generating is sensical, is data that actually is accurate and sensible for the language. So the first technique that I want to talk about is called back translation. In back translation, we translate a sentence from the target language, from the source language to the target language, and then back translate from the target language to the source language, typically using a different machine translation model. So in doing so, you may create a new source language sentence that is slightly different from the original input sentence that you compare with the target sentence and augment the training data. In this example, we have an English sentence, "I am hungry," and we want to translate it to a low resource language. And this time I chose the low resource language Quechua, which is a widely spoken indigenous language in Peru. And when we perform the translation, "I am hungry," to Quechua, we get this translation. And when we back translate that sentence, we get the English sentence, "I want something." So "I want something" is not exactly the same sentence as "I am hungry," but it is a sentence that is potentially portraying the same meaning as the original sentence. And so then we compare "I am hungry" with the translated sentence and "I want something" with the translated sentence. And now both of those parallel sentence pairs can be added to our training model. So when we're performing this back translation, the idea is that we're starting with sentences where we already know what the translation is, but we're asking a machine learning model or a deep learning model to make the translation for us, and then translate back to see if we get something that's slightly different that we can then use as an additional line in our training data. Here is an example of actually performing back translation. This is using the Hugging Face transformer pipelines. And I have chosen two pre-trained models from Hugging Face. The first pre-trained model was trained to translate English to French, and the second model was trained to translate French to English. So I start with a sentence in English. In this case, this is an English sentence, is the sentence I chose. And then using the Hugging Face pipeline, which I've set up for each of the target and source languages, I can perform an initial translation, so that is going in the first direction, and then the back translation using the second model. So in the first case, I'm using the English to French model to translate my target sentence into its French equivalent. And in the second case, I am taking that translated sentence that has now been translated to French and using the second model, which translates French to English, to back translate that sentence back to English. And the hope is I will get a sentence in that back translation that is a different sentence but conveys the same meaning. And then I can use that new sentence pair in my training data. So printing these out, I've put here what the output looks like. So we start out by outputting the initial sentence. This is an English sentence. And then we print the translated sentence, so the first step of translation of English to French. You see the outcome there, c'est une phrase anglaise. And then finally, we employ the second translator model by using the French sentence now as input and translating that back to English in the second model, and that translation translates to it's an English phrase. So this is an English sentence and it's an English phrase are similar sentences. They convey the same meaning, but they are syntactically different. So now in our training data, we have the alignment of this English sentence with this French sentence, and then a second data point where we have an alignment of this English sentence with this French sentence. And so you can see how doing this repetitively by doing back translation using different models, we can get more sentences that we can add to our input corpus for training. And again, being very aware that in doing so, we might end up with a nonsensical translation, so we have to be careful to watch for that. In addition to data augmentation, you can use back translation to highlight translation errors. For example, if I take a sentence and translate it using one model and then back translate it using a different model, if I were to get a sentence that is nonsensical, that highlights a potential error in the translation with one or maybe even both of the models. So for example, if I ensured that if I was trying to improve the accuracy of my model that did the first translation, I would do the back translation with a model that I knew to be accurate, and that would help me determine where my model is in need of improvement. So back translation is just one technique for augmenting your training data set. Some other techniques include source modifications. There are a lot of different kinds of source modification techniques, but in each of these, the idea is that you modify the original source sentences. So you have your limited training data set where you have source sentences and target sentences, and you want to modify the source sentences in such a way that the sentence has changed but has the same meaning with new syntax, and then you can align that new sentence with the same target sentence that you had in your training data. You can also employ source modifications in concert with your back translate sentences while creating new sentences that preserve meaning. A few different approaches to modifying the source sentence include lexical changes. So if you recall, lexical relates to words, and in lexical changes, we can replace words with their synonyms. For example, using a thesaurus, we can replace a word with a synonym that has the same meaning. and does not change the meaning of the sentence. You can also have techniques where we employ word embeddings, and we find, so instead of taking the word as is, we take the words that have already been embedded using an embedding model and find statistically similar word embeddings. So that would be an alternate to using a thesaurus on the actual words. Or we can use contextualized word embeddings. And I point to just 2 papers here that use contextualized word embeddings that you can review for more context on that methodology. We also have the ability to perform morphological changes on a sentence. So that would be things like changing the prefixes, suffixes, and tense of a verb. So you can imagine taking a sentence that is in present tense and creating the same sentence in past tense or future tense, or changing prefixes and suffixes as they relate to the tense of the sentence to help build up a set of input sentences that are similar but show more meaning across the language. You'd have syntactic changes where you shuffle, where you look at the syntax of the language. So that would be related to the grammar of the language. And in some languages, you can actually shuffle the order of words. And if your language is flexible to shuffling, where changing some word orders results in a sentence with the same meaning, meaning that the initial word order did not matter in the meaning of the sentence, and if we shuffle the words in a different order, we get the same meaning. In a language that allows that, we can use that technique to create new sentences. We can also split or merge sentences where allowed by the language, so to create shorter or longer sentences. So you can imagine a long sentence broken down into 3 short sentences, or some number of short sentences where the same meaning is conveyed, but the shorter sentences are more concise. Or you can take shorter sentences and use whatever grammatical techniques are available in the language to combine those sentences, for example, with commas, semicolons, and words like and or, to build up long sentences from shorter sentences. So then you can take the original sentence, which you will still have in the language, and augment the data set with the new longer and shorter sentences that you've created by applying the grammar of the language. You can switch from active to passive voice, and you can play with negating sentences to generate a new sentence that has the opposite meaning of the original sentence. In addition to source modifications, we can do text generation and automate that by training a machine learning model. So train a model on existing sentence pairs, so that model can then generate text in new variations in the source language. And so that is a way to augment the source language text in an automated fashion using a trained model. And finally, you can do noise injection. So if you inject noise into your input data set, you can keep the original data, the non-noisy data, but then add to it some data where noise has been injected in the form of, for example, spelling errors or some minor word replacements. So where a human speaker may use the wrong word, but you can still tell that the sentence has roughly the same meaning, but the human speaker chose the wrong word. So in addition to spelling errors, for example, the word to in the English language, T-O, T-O-O, T-W-O, those are all different words to, and choosing the correct word in a sentence is commonly an error that you see in human generated text. So by injecting that noise and adding those additional incorrect sentences with spelling errors or minor word replacement, like the to example, now you have created a larger data set. And not only that, your larger data set could result in a model that is more robust to those imperfections that we do actually find in real data. So when you're training a model based on data that has been augmented with noisy data, you may end up with a more robust model than you would have otherwise. So those are just some examples of doing data augmentation to grow your training data set. Another thing that you can do is train the initial model to be multilingual. So a lot of the models that you look at that have been pre-trained for language translation were trained to translate from a source language to a target language. If you train a model to be multilingual versus bilingual, then that model can be trained on parallel sentences in many languages instead of just a single source and target language. And there you would, as your training phase, input bitexts, so parallel texts of the many language pairs across your languages. And you would add a token to the encoder in your translation model that specifies what the source language is. And in doing so, you have trained a model to be able to do translation across multiple languages. So you have a multilingual trained model. And that gives you the benefit of applying low resource languages, where if you have a model that is multilingual and has been trained with higher resource languages that are similar to the low resource language that you're trying to capture, then that model may be capable to translate in that low resource language as well. And when we talk about a model's ability to translate, we should specifically talk about how we evaluate that model. So we can apply all of these techniques and see if we can improve the translation of the model, but how do we know if we have improved translation? And to do that, we need to specify how we are going to evaluate the goodness of the model. An evaluation in machine translation is concerned with a couple of things. First of all, adequacy. How well does the translation capture the exact meaning of the source sentence? So its fidelity or its faithfulness. So whether or not the syntactic correctness of the translation is captured correctly, adequacy says how well does the translation actually capture the exact meaning. So you could have a translation that is syntactically correct but does not capture the meaning of the source sentence well. Another concern that we have for evaluating is fluency. So how fluent is the translation in the target language? And so that goes back to the accuracy of the grammatical structure of the language. Is the translation clear? Is it readable? Does it come across as natural? Would we expect to see the sentence like that in the language? And that deals with the fluency of the translation. So a translation can be fluent but not adequate, or it can be adequate but not fluent. So those are two different things that we would want to look at in terms of evaluating how good your model did a translation. So how do we actually perform the evaluation then? A couple of options you can look at. One is to have human raters. So that would be what has been going on since before we had models. Having human raters look at different translations and make the determination if that was a good translation or not. But then, of course, we also want to look at ways that we can do automated evaluation to look at the performance of a model. So I have posted here some pros and cons of human versus automated evaluation in machine translation. So if we start by looking at human evaluation, the pros would be higher accuracy. So humans are able to assess the fluency or naturalness or even the cultural appropriateness of the translation. So where a machine may not be able to see if something's culturally appropriate, a human should be able to determine that. Humans will be more flexible in their ability to evaluate a translation. They can handle more complex sentence structures and errors that might be more nuanced. And of course, a human can provide insights into the user experience because the human being the user of the translation ultimately. If we look at the cons of automated evaluation, the pros of automated evaluation, of course, the first pro is that automated evaluation is going to be fast and scalable. If we use automation, we can evaluate large data sets very quickly. The objective, it uses consistent metrics. So when you look at humans, the metrics may be inconsistent. If we do automated evaluation, those metrics can be applied consistently across the text that we are evaluating. And of course, automated evaluation may be more cost-effective as you do not need human evaluators if you're doing purely automated evaluation. But let's look at some of the cons, though. The cons of doing human evaluation include it is time-consuming and expensive. Of course, it's time-consuming because humans are going to be slower at reading through the translations and evaluating their adequacy and fluency. And it's going to be expensive in terms of employing the humans to perform those tasks. There is some subjectivity that comes into play when we're dealing with humans. So evaluators may have different preferences in how they would expect the translation outcome to be. And using humans is not particularly scalable because it's difficult to evaluate large volumes of translations. You would either require a lot more time or a lot more humans applied to the challenge to make it scalable. Of course, there are also cons with automated evaluation. Limited accuracy, so automated techniques may not capture fluency or cultural appropriateness. Automated techniques may have difficulties with more complex sentences and struggle with nuanced errors. And of course, automated evaluation is not going to reflect user experience because the automated machine is not the end user, and so it doesn't really assess naturalness for humans, meaning how natural is that translation for a human to read and understand. Ultimately, the best approach to evaluation is often going to involve a combination of human and automated methods. So automated evaluation can be used initially to pre-screen very large data sets and do the initial analysis of the accuracy of the translation, while humans can then take the results from that and do a more in-depth analysis and provide the final judgment on how fluent and adequate that translation was. So the best approach will often be to combine both automated evaluation with human raters who ultimately make a final judgment on the goodness of that translation to determine which models are better at translating. When we talk about actually doing the analysis, we need some metrics that we can use. So some common evaluation metrics include BLEU, which stands for Bilingual Evaluation Understudy. And this is a function of n-gram word precision over all the sentences, combined with some penalty they call a brevity penalty that's computed over the corpus as a whole. And we'll look at this in more detail in a minute. Another evaluation metric, CHRF, which is character F-score. And this is based on the idea that a good machine translation will tend to contain characters and words that do occur in the human translation of the same sentence. Of course, these evaluation metrics are used in automated evaluation, and the shortcomings of the metrics include a limited focus. These scores primarily focus on n-gram precision, or the n-gram overlap between translated and reference text, so they don't directly evaluate fluency, naturalness, or even semantic accuracy. They're also sensitive to order, so the metrics can penalize translations that have a slightly different word order, even if the overall meaning is correctly conveyed. There is inconsideration of nuance. They struggle to capture the subtleties of human language. which includes synonyms, paraphrases, and other cultural references. And there's potential gaming. In some cases, a high score can be achieved by a translation that is grammatically correct, but is really not natural or doesn't fully capture the original meaning of the translated sentence. For further reading on this, let's look at BLEU described on Google Cloud. In understanding the BLEU score, we see the definition that this is a metric for automatically evaluating machine translated text, and the score is actually a number between 0 and 1 that measures similarity of the machine translated text to a set of high quality reference translations, where a value of 0 means that the machine translated output has no overlap with the reference translation, so it's of low quality, while a value of 1 means that there is a perfect overlap with the reference translation, and then the translation is considered to be of high quality. And it has been shown that these scores do correlate well with human judgment of translation quality, and take note that even human translators do not achieve a perfect score. So the way to interpret the BLEU score, first there's some warnings. Trying to compare these scores across different corpora and languages is discouraged, and even comparing the scores for the same corpus but with different numbers of reference translations can be misleading. So the score is really used as a rough guideline, and you can use this chart to interpret the meaning of the score. For example, a score less than 10 means that the interpretation is almost useless. 10 to 19, it's hard to get the gist of it. 20 to 29, where the gist is clear, but it does have significant grammatical errors. 30 to 40 roughly translates to it's an understandable to a good translation. 40 to 50 is high quality. 50 to 60 is very high quality, so this would be an adequate and fluent translation score. Greater than 60 on this score says loosely that the quality could be better than human. So here's a nice color gradient chart that you can use as a general scale to interpret the score of your translation if you're using the BLEU score, where red is bad and green is good. And this site also provides some mathematical details to define how the BLEU score is calculated. So you have the mathematical calculation, which includes the n-gram overlap, which we talked about, and then how the brevity penalty is calculated. So this penalty described here, it penalizes the generated translations that are too short compared to the closest reference length using an exponential decay. So the penalty compensates for the fact that the score has no recall term. And precision is defined here as well, and how the n-gram overlap is actually computed. So that is a nice reference, and then of course we have some examples here of different translations from sentences with their BLEU score. So that's a nice additional documentation to follow. And that covers an overview of just part of the ways that we can look at training in low resource environments and evaluating the accuracy of our models, whether or not they were trained in a low resource environment, but models trained in general, evaluating their accuracy is a problem that is quite necessary, of course, in machine translation and doing research and even choosing a translation system.